So the chapter 3 test is coming up. It is on differentiation. So everybody needs to have out something to write with, whether it's on your iPad or paper. You'll turn this in as soon as we're done. Okay. So where it says chapter 3 test review number 2, this is going to be chapter 3 test review number 2. I know we haven't done the first one yet, but the first one there's a video already posted, so we're doing this one first. So this is review number 2, just like it says up on the board. Okay, so we are going to is that how you spell that word? Differentiate. I think so.
Looks about right. Let's not actually.
So we are going to be differentiating stuff. When you do it, you do not need to go further than our first step. Okay, so here's some easy ones. Remember your rules of polynomials. Just take the power rule for each individual function. So that would be 2x plus 3. I will have some where I combine some trig stuff. So look over your trig functions. So the derivative of all of your trig functions are necessary to make sure you look over. So this would just be 24x plus the cosine of x minus the secant squared of x. So make sure you know that. But make sure you know that if we have, say, that 12x squared touching the sine of x, let's make it the sine of 2x. We will have to, for something like that, we will have to use the product rule. So make sure to put yourself a nice little dot between everything so that you remember when you do the product rule, so you can kind of clearly see what your first and second pieces are. Now, once you do the product rule, I don't need you to go further for simplification. When we get into chapter 4, we are going to have to simplify it more than we are doing in chapter 3, but for this purposes, So let's go ahead and do our product rule. So it is the first times the derivative of the second. Now remember, the derivative of a sine is a cosine. So it has a function locked in it. So it is the cosine of the stuff times the derivative of the stuff. So some of you were trying to do the inner derivative too quickly. The stuff stays there, and then we multiply by the derivative of the stuff. So the derivative is 2. And then plus the second times the derivative of the first. So just be careful. Make sure you look over your flashcards before we take the test. You will also need to know a quotient rule. So let's do one that has a quotient in it. So if we're doing that derivative, the first step I would take if I were the person doing it is I would put my top and bottom in parentheses, just so you kind of had a clear way to do that. Now I need you to use parentheses as you go through the quotient rule, or you're technically it's not quite correct algebraically. So just keep that in mind. So when you do that derivative, you are going to do the bottom Don't change it. It's just the bottom. Times the derivative of the top. Now, the top is a nice one. That's just 2x plus 2. Now, it's always a minus the top times the derivative of the bottom. Now, be careful when we do the bottom here. The cosine of 2x does require a chain rule. So when we do that cosine of 2x, remember, you're going to make that a negative sine of 2x. Keep the stuff. Times the derivative of the stuff. The derivative of a secant, you guys are sometimes not quite writing it correctly. You have the right idea, but it is just the secant times the tangent. Just the secant of the stuff, tangent of the stuff. Okay, so that is, now let me go over it again. It is the bottom times the derivative of the top minus the top times the derivative of the bottom, all over the bottom squared. Okay, so let me just go over it again. It is the bottom. Don't change anything. It's just write the bottom in parentheses times the derivative of the top in parentheses minus the top times the derivative of the bottom in parentheses. The derivative of a cosine is a negative sine of the stuff. Leave the stuff as is times the derivative of the stuff. Plus the derivative of a secant is a secant tangent all over the bottom squared. Now, I don't expect you to go any further. I don't expect anything more than that. That's what I need, okay? Hopefully I haven't forgotten. Okay. Let's talk about when we have some radicals. So we have the fourth root of the tangent of 2x plus 3x squared. The fourth root of the tangent of 2x plus 3x squared. Now this doesn't count, of course, as differentiation, but a rewrite is helpful for this one. So make it the tangent of 2x plus 3x squared, all to a 1/4 power. So that's what I would do before I proceeded. Now, you can kind of do that in your head if you remember that rule, you're welcome to. But that's a really good rewrite before we do the derivative. So how do we do the derivative of this? We drop down to 1/4. The stuff stays there. We drop the power down by 1. Times the derivative of the inside. So now it's where we take the derivative of the inside. The tangent is a secant squared. That is a secant squared of the stuff times the derivative of the stuff plus the derivative of a 3x squared, which is a 6x. Now, I wrote 1/4 minus 1. I'm going to give it to you if you write it like that. If you write negative 3/4, that's also correct. I don't care, okay? So let's look over what we did again. Power drops down in front, stuff stays there, power goes down by 1, derivative of the stuff. And then the derivative of the stuff has to use whatever rules apply to that particular thing that's stuck inside. Everybody good with that one? Okay, let's keep going. Let's say we have a fraction to the 4th power. You're not doing the quotient rule. Now, there are some rewrites. I saw some people in the past have written that as x plus 1 to the 4th on top and x minus 1 to the fourth on the bottom, and then did the quotient rule that way. That does work. So there are things you can do, but this is what I look at when I see that problem. I think of it as a chain rule. I think of it, drop the 4 down in front, leave the stuff, power goes down by 1, times the derivative of the stuff. So that stuff happens to be a quotient. So that stuff requires that I do the quotient rule to that stuff. So that stuff is bottom times the derivative of the top minus top times the derivative of the bottom all over the bottom square. And I don't need you to do anything. Now there's going to come a time where we will practice making that look nice. But for our purposes, it is what it is. Okay. Everybody good so far? Okay. So now let's do an implicit. So let's say we have this. Okay, so we've got this function, and it's really difficult for us to be able to explicitly solve it for y. Okay, so the derivative of a 2x squared is a 4x. This is a product rule, Mrs. Hott. So we're going to do the first times the derivative of the second plus the second times the derivative of the first. There we go. Is that what you were missing? And then here, this is 2y prime. This is 5. This is y prime. Okay. Does that look better? Are we good? Okay. So every piece that contains a y prime going to go to the left. And the pieces that do not have a y prime are going to go to the right. So if we keep the y primes on the left, we're going to get 2y prime minus 3x y prime minus y prime. On the right, we're going to get a 5 plus 3y minus 4x. That's better. Okay, now at this point, we're still going to do the same thing. We are going to take out a y prime. When we do that, we are left with 2y minus 3x minus 1. Now that parenthesis there is multiplying by y prime. I want the y prime to be by itself. So if I want the y prime to be by itself, I've got to divide that off. So our final answer would be 5 plus 3y minus 4x all over 2y minus 3x minus 1. I think there we go. We should have that one okay now. We are going to need to know our rules of ease and logs. We haven't practiced a lot of those. So let's go ahead and practice those. Yeah. There we go. Okay. So remember, a derivative of an e is just an e to the x. So the 2 just comes along for the right. Remember that the derivative of a natural log is 1 over x. So this is just going to be 5 times 1 over x. Or you could also write it as 5 over x. Now, those are the easiest cases. So let's look at some that require a little more thought. Same ideas, but just a little more stuff to them. Okay. Let's say we're taking the derivative of that. It's a product. Put a dot between it, and let's do the product rule. So it is the first times the derivative of the second. Now, an e to the 3x is an e with a function in it. So it stays the way it is. The only thing you have to tack on is the derivative of the function. So the derivative of 3x is 3. Plus the second times the derivative of the first. So that's not so bad. What's if we have e by itself with a function in it? The derivative of that is going to be same thing, don't change a thing, times the derivative of the function that was stuck inside the e. So the derivative of that power, and so that's going to be 2x plus 5. So e's are nice. They're natural logs are a little harder. So let's do another, we want to do a few natural logs, and then I want to do a log that isn't a natural log, but a different base. So let's do x natural log of x. Let's do x natural log of 3x. Okay. Now, it's still going to require a product rule. Still going to require a product rule, so put a little dot between them. So we're going to do first times the derivative of the second. Well, that's a natural log with a chain rule. It's still 1 over that thing times the derivative of that thing. 1 over that thing is the way natural logs normally work, but it's 1 over the function times the derivative of the stuff. Yeah.
So if it was just x times the natural log of x, it would be 1 over x times 1.
Yeah. And then plus the second times the derivative of the first. Now this cancels out nicely, but I don't care. Just leave it. Okay. Now let's do some natural logs or logarithms that aren't natural logs. Okay, so let's do a log base 2 of x to start. Let's do a log base 2 of x. Now, logarithms work like logarithms work. It is just 1 over the inside. But when it is a log base 2 and not a natural log, just multiply that by the natural log of whatever that number, that base is. So it's just times the natural log of that thing. That's the only difference, okay? So it's 1 over x times the natural log of 2. If this base here was a 7, it'd be the natural log of 7. If this base here was a 10, it's a natural log of 10. And it all comes from the change of base formula. That's where it comes from, okay? So now let's do one that it has a little more stuff to it. So let's say it's the log base 2 of 3x plus 7. The derivative of that is just 1 over that thing times the natural log of whatever our base is times the derivative of that thing. So let me go over that one more time. It'd be 1 over that thing. You always tack on the natural log of your base times the derivative of the stuff inside. And if you want to make that prettier, fine, but I'm good with that. Okay. Let's go back up to this problem. So I'm going to move this problem maybe. Yeah, okay. Okay. So let's just revisit 7 for a minute. If I tacked on, which I will, a second piece to this question, if I said find the equation of the tangent line at the point, and I don't know what a point is that's good, but let me tell you, we're going to try. So at the point 4, that's the point 4, 1. Okay. Okay. So if you want the equation of a tangent line at a point, I'll give you the point that touches the curve at a particular spot. What we have already found is that y prime equals 5 plus 3y minus 4x over 2y minus 3x minus 1. Now remember the steps of finding the equation line, no matter what we've done so far. First step, you find y prime. Second step, you plug in the point to find the slope. Third step, you use y minus y1 equals m times the quantity of x minus x1. That's the steps every single time. So we've already done the work in 7 to find y prime. So the only thing left now to do is to find the actual slope. So wherever you see x, we're going to put a 4. Wherever you see y, you're going to put a 1. So on top, that's going to be 5 plus 3 minus 16. On the bottom, that's going to be 2 minus 12 minus 1. Let's make sure I did that right. Okay. 5 plus 3 minus 16. 2 minus 12 minus 1. Okay. So on top, we get negative 8. On the bottom, we get negative 11 for a slope of 8/11. And then the last step, you just have to set up the y minus y1 equals m times the quantity of x minus x1. I don't expect you to simplify it down further. So it's y minus 1 equals 8/11 over x minus 4. So that would be your answer. Okay? So make sure you understand. And we could have done that with any of our equations. If I said find the equation of the tangent line for any of them at a certain point, you would do the same exact step. If you knew the derivative, you stick in the point, you find the slope, then you use the point slope formula at that point. Everybody good with that one? T plus 1 to the negative 2. And S is in meters, and T is in seconds. Okay. So they claim that is the position function of a freight train. Okay. So it says find the velocity and acceleration functions. Okay. So the first thing, let's talk about the velocity function. The velocity function, remember, is just the first derivative. So you are going to drop the power down in front. That constant just hangs along for the ride. Stuff stays there. Power goes down by 1. Find the derivative of the stuff. Okay. So that is our first derivative. Now, it also says to find the velocity at time 6. So let's make this look a little nicer. 100 times negative 2 is negative 200. And then we have t plus 1 to the negative 3. So they said, what is the velocity at time 6? So let's go ahead and plug that in. Okay. And so the velocity at time 6, you're just going to plug that in. That would be negative 200. 6 plus 1 is 7 to the negative 3rd. Now, I don't expect you to do anything but make it nice enough, just if it's fractional like this one, simplify it as much as possible. So that'd be negative 200. And 7 to the 3rd, is it 243, 2 something? 343. And that doesn't reduce. That is what it is, okay? And so that would be in meters per second. So at time 6, it's slowing down. Its velocity is negative 200 over 343 meters per second. Now then, it also did ask to find the acceleration function. The acceleration function is the derivative, one more time, it's the derivative of the velocity, or you could even say it's the second derivative of our position. So here is the kind of most simplified, nice version right here. So let's use that one. The negative 200 stays there, negative 3 drops down in front and makes it a 600. Stuff stays there, power goes down by 1, times the derivative inside. Now, the derivative of t plus 1 is just 1, so why write it? And then they said, what is the acceleration at time 6 seconds? So let's plug 6 into that. That would be 600 over 7 to the 4th power. And that is 600 over 2,401 meters per second squared. Why they pick 6 when nothing made it look nice after that? Yeah. So just remember, main takeaway from that, the first derivative of position is velocity. The second derivative of that is your acceleration, okay? So your test looks very similar to what we have just seen. And then we'll review one more time tomorrow. Keep this and turn in a copy to where it says chapter review number 2. Sorry, we're doing number 2 before number 1, but there you go. Okay, so just take a picture of it and then put that into Google Classroom. And then guess what? Maybe study some of these rules. Study your flashcards. So for the remainder of class, study some of the rules that you had forgotten. There you go.